Okay, so we are moving on to a new topic. This is called implicit differentiation. And what I did is I went ahead and put some background information in for you. So I'm just going to go ahead and read through some of this important information here. Highlight with me, make notes with me. Every function we've worked with so far are called explicit functions. And explicit functions means that it's very clear what the dependent variable is and what the independent variable is. In other words, the equation is already solved for y. So in any of these three examples, we have y equals, okay? However, there are also functions called implicit functions. And this is a function in which the dependent variable is not isolated on one side of the equation. And so, for example, an x squared plus y squared equals 25. I would have to do some manipulating in order to get that y by itself. So see here, it says the graphs of implicit functions are usually the union of graphs of two or more differentiable functions. In other words, if I were to go ahead and isolate this equation up here, this x squared plus y squared equals 25, if I isolate that for y, I'm going to get this equation here. This y equals plus or minus square root of 25 minus x squared. And, it's been a really, really long time since I have taught geometry. But back when I taught geometry, we graphed equations of circles. And actually, I'm in Algebra 2 trig as well. And really what this is this is the equation of a circle. And it gives us the two halves to the circle. And so what this gives us is this top part gives us the equation y equals the square root of 25 minus x. And the bottom half gives us y equals negative square root of 25 minus x squared. My apologies. I forgot a squared up at the top, okay? And so when I get this plus or minus, remember when you solve by taking the square root, you need plus or minus. I'm actually getting two parts to this circle. Now, if I were to ask you to find y when x is equal to 3, that means I would substitute 3 into this equation. And again, due to the plus or minus, I would get a plus or minus 4. And so just want to point that out on my nice little circle graph. That means I would have the ordered pair 3, 4, or I could have the ordered pair 3, negative 4, okay? Those are both on the graph of this function, okay, of this circle. If I say find the slope of the tangent line for this function, x squared plus y squared equals 25 at the point 3, 4, I would have some manipulating to do in order to do that. Now, if I take a look, the equation of the tangent line, or the slope of the tangent line, at 3, 4 is going to be a negative slope versus the slope of the tangent line at 3, negative 4 would be positive. So it is important with these explicit functions that we know the entire ordered pair that we are working with, since it's possible that you have x values that share multiple y values. Now, because I already went ahead and isolated the y up here, I can simply take the positive version, the y equals the positive square root of 25 minus x squared, and find that derivative. And that's what I did for you in this first set. It says, let's find the slope of the tangent line. We have to use the positive square root function. So I worked through, here's my derivative. After being simplified, I evaluated at 3 and got negative 3/4. In other words, the slope of this tangent line here is negative 3/4. Okay, but this next section says you may not always be able to easily solve for y to find an explicit function. That means that we need a way to find the derivative of an implicit function. So this top example of this circle, it is easy to isolate that y, therefore making it easier to find the derivative, as long as I know what point I am finding the derivative at, okay? Which part of the function to use. However, as you have learned in this course, if you have not learned previously, life is not always that easy, okay? oftentimes you have implicit functions that are not very easy to take the derivative of. And so we need a method that's going to help us do that, okay? And so let's look at the same function, x squared plus y squared equals 25. And we're going to take a derivative of this function in this form. So we're going to keep it in this implicit form, and we are going to find the derivative. Now take a look what this says. This method requires the use of the chain rule, okay? We can think of y as an f of x hidden in our equation. You must really follow along with me here at this point, okay, to keep up. Okay, and so what that means is instead of writing the x squared plus y squared equals 25, I'm going to write x squared plus f of x, that's being squared, equals 25. I'm doing this because I really want you guys to see where this chain rule is going to come into play, okay? Now it says to differentiate, take the derivative of both sides. So I'm going to go ahead and I'm going to practice some proper notation here in doing this. Now when I say take the derivative of both sides, what that means is I'm taking the derivative of x squared with respect to x. I'm taking the derivative of f of x squared with respect to x. And I'm taking the derivative of 25 with respect to x. And I'm doing this this way for two reasons. One, I want to show you that you're really applying the derivative to each term. And that's what we've been doing all along. That was one of the properties from the beginning, that we take the derivative of each individual term. And two, I just want to point out that we are taking the derivative where x is the independent variable, okay? I am taking the derivative with respect, to x, which means that I am applying the derivative to x variables. Now I know how to take the derivative of x squared. The derivative of x squared is 2x. And I know how to take the derivative of a constant. The derivative of a constant is 0. But I think that I need a little bit of help taking this derivative. Well, it looks to me like I have a chain rule. It looks to me like I have an outside function, x squared, and an inside function, f of x. And notice that my variable that I'm dealing with is an x variable, so it seems reasonable to apply this derivative. All right, the derivative of x squared is 2x. Whatever was inside of that x, though, stays inside. So it's like saying 2 times f of x, okay? And that was the derivative of x squared, times, now I need to take the derivative of f, and the derivative of f is just written as f prime, okay? And so that's my derivative of that f of x term, but let me put that back in terms of y. Okay, so I'm just going to rewrite this whole thing. I'm going to write it with the y though. So I took the derivative of x squared, that's 2x. I took the derivative of y squared, and really what I got was 2y times y prime. That's the equivalent of writing f of x is y, and the equivalent of f prime of x is y prime, and this equals 0. Okay. Now, I know it does say down here that we're going to go ahead and solve for f prime of x, and f prime of x is the same as saying y prime, and evaluate at that point. We should get the same derivative that we did up here. Okay, so just to review this again, what I did is I took this y squared in the original, and I wrote it as an f of x instead. Because when I take the derivative with respect to x, it's just easier to understand that I'm taking the derivative of an x variable. After I was done taking that derivative, I converted my f of x and f prime of x back into y's and y primes. And now I'm going to go ahead and take this derivative, 2x plus 2y times y prime equals 0, and I'm going to isolate the y prime, okay? And so that means I'm going to subtract the 2x on both sides, and I'm going to divide by 2y on both sides to get that y prime is equal to negative x over y. And it says to evaluate at 3, 4. Okay, so I'm going to say, okay, y prime, when I evaluate y prime at 3, 4, I'm going to put the 3 in for x and the 4 in for y, and therefore the slope of the tangent line to this original implicit function at the ordered pair 3, 4 is negative 3/4. We already said that that matches the graph that I have up above here, okay? That tangent line would appear to have a negative slope. Okay. So I'm going to go ahead and flip the paper over, start a new video, and work through some examples with you.